All right, welcome everyone to another edition of the RAD colloquium. Very nice to have the person again, and very nice to have Rick speak to us again. So it's kind of difficult to introduce Rick because he's worked on everything and worked with everyone.
That's a total lie.
But in a nutshell, I believe Rick was the VLA's very first postdoc.
That's right.
Tasked with the very general problem of calibrate this thing. No one knew any idea how to do that at the time, and so Rick was the postdoc tasked with calibrating the VLA. So it's probably fair to say that he knows a few things about the VLA and a few things about calibration. He's worked on a lot of things since. I think he loves Cygnus A, although this talk is not about Cygnus A.
Not today. No, that's another day. Yeah.
Rick was also the chief scientist for the EVLA upgrade.
Project scientist is himself. Yeah.
For VLA upgrade, yeah. And he's also, I'm happy to say, a visiting professor at RAD. So visiting again, as he often does. And it's very nice to be able to hear him give a talk. And he's going to speak about some work he's been doing jointly with Ben and Sarah here on basically on polarization. So Rick, if you're good to go, you may start. Remote people, if you have questions, please put them in chat or raise your hands. We'll have a question and answer afterwards. And now I give you Rick.
Yeah, well, thank you, Ole. It's a great pleasure to be here again. I've made quite a few visits to South Africa since Ole and I started working on some problems, maybe 6 or 8 times. Lose track after a while. So the general thing that we're working on is I like to call this precision polarimetry. We're trying to get polarimetry beyond the roughly 1,000 to 1 dynamic range that polarized images seem to be limited to. And so I'm working here with Oleg and Jonathan on one aspect. We won't be talking about that today. But as a sort of a side issue, Ben and I and Brian Butler, who is a staff member at NRAO, and he's an expert on planetary physics, which, as you will see, is an important aspect of things, have been running into working on another project, not directly related to precision polarimetry, but necessary in order to check our results and to see how well polarimetry actually works. And this is on the electric vector position angle. That's what EVPA is used to stand for primarily 3C286, but a little bit of work on 3C138 as well. And this is, we stumbled into this work, not because we were looking for answers, but because some inconsistencies were found and some remarkable things that we've learned. So first, I want to point out a few things about 3C286. This is a remarkable radio source. Here where this slow-moving cursor is an image made with the VLA with about 150 milliarc seconds resolution of the well-known calibrator 3C286. There is a bright nucleus up here. This thing is useless here, which is highly polarized, about 12% polarized emission. There's some inner structure in here and a very faint. This is not a linear scale on here. So the amount of flux in these extended emission here is only a few percent of the nucleus. It is strongly dominated by this internal structure here associated close to the nucleus. And 3C138 is a similar object. This one is high resolution, 70 milliarc seconds. The nucleus is here and it's not polarized. And this is a highly polarized jet-like emission. Both of these sources are heavily used for polarization. And why do we need polarization in calibrators like this? Because the VLA uses a circular feeds. And so there is no preferred angle when you have circular feeds. Rotating a circle is still a circle. That's one way of looking at it. And so in order to fix the cross-hand phase, which sets the position angle in circularly polarized systems, you need to observe a calibrator of known polarization. And 3C286 has been used for decades as the known highly polarized source. It's compact and it is incredibly stable. In 40 years of monitoring it, I have not been able to detect any flux change at on any frequency between 1 and 50 gigahertz. And what you might wonder, how can that be? And the answer seems to be it has no nucleus, even though you see very compact structure up here. VLBI shows no flat spectrum emission. It is simply a polarized little bar on the sky. Presumably the nucleus is turned off or the jet is facing away, and it has left some very small scale, highly polarized structures. All right, this source is entirely different. That 3C138 is highly variable, and that's a problem because it keeps changing its flux and also changes its polarization as flares are coming out of this nucleus and they're polarized in their own way. So that's so we won't be speaking too much about that. For linear systems like MeerKAT, you don't actually need to observe a known polarized source, because the position angles are set by the orientation of the dipoles of your reference antenna. So, but that might be wrong. The engineers are not perfect, and these feeds might be misoriented by a few degrees. All right. So anyway, so all this introduction was that for the VLA, we have to have a known polarized calibrator. And for linear systems like in MeerKAT, you don't need it, but you'd like to have it to be able to check your answers. So moving on, and now I can't seem to change my page.
You might need to stop your share and reshare again.
Oh, no,
I know, but the room's been up all the
yeah,
time.
it's been on
No,
there. It's video still.
It's not, I can't advance. Yeah.
So you might have taken over your.
I just did it. All right. What did you do to make that happen?
With the mouse, I think the mouse was focused. Anyway,
I think Zoom stole your focus.
All right, never mind. Okay. All right. So 3C286. Since at least the 1970s, all of us have just been told that the EVPA of 3C286 is 33 degrees. And it's been taken as truth for decades. But is it? Where did this number come from? Well, it turns out that at this telescope, the ARO, which is in Ontario, and incidentally was the first radio telescope that I used in 1967. I was there as an undergraduate. This was used by Carl Bignell and Ernie Sequist in the early 1970s to measure the intrinsic position angle of 3C286. And they did it in a very interesting way. This telescope has a single dipole feed, which is on a rotatable turnstile. So the feed just rotates about once, I think it's about once every 2 minutes. And everything was analog, and out came a chart record in which you got a nice sinusoidal wave. The amplitude and the phase of that wave tells you what the fraction of polarization and the position angle. And they published a paper, which I've looked at from 1973, which said 33 is the answer at 6.7 and 10 gigahertz. And I didn't do a very deep literature search on this issue, but but I do believe that the fact that the two numbers were the same of those two frequencies within 1 degree, and it was written into the software everywhere as far as VLA and probably other places, that 33 degrees is the right answer. And all VLA observations since then have used 33 degrees. So, but I could find nothing on how correct this is, and is there any variation in frequency? And the only way you can do this with our systems is to find a source whose electric vector position angle is absolutely known without reference to anybody else's work. And so what can you do for this? What kind of object can you find? And it turns out the best thing to use are planetary bodies. So let's take a look at this kind of business. Thermal emission from solid bodies. When I first learned about this, I was quite amazed, because I had always thought from, I don't know where, that a solid body is unpolarized. It has no emission from, say, Mars or the moon. You should measure zero polarization. It's a solid radiating body. But this is not true in detail. It's true overall, but not true in detail. Now, to understand this, we have to mention a couple of things. when you look at the moon and the optical wavelengths with your eyes, you're seeing scattered solar radiation. You're not seeing the moon's own emission. That is orders and orders of magnitude lower. And so everything that we see optically on these things is illuminated from the sun. But this is not true in the radio. When you get down to objects that are in hundreds of degrees, the radio dominates. But it is important to realize that the radio emission that we're seeing from the moon does not come from the surface. It comes from 10 to 20 wavelengths down into the surface. So the a tau equals 1, the optical depth of one layer is centimeters to meters deep, depending on what frequency you're looking at. And it's the transfer of the radiation from below the surface across the boundary into free space that gives a very characteristic signature. So you look at it this way. So here's the planetary body. Radiation is propagating upwards. As everybody knows here, it's the transverse phenomenon. And there's two components of the transverse electric field, one of which is in and out of the plane, and the other one is in the plane of this diagram as the ray transfers. When it reaches the boundary, you get a reflected portion and you get a transmitted portion. And the interesting thing is that the fraction of the power which is transmitted and reflected is different for the two polarization components. And it's a function of the angle at which the radiation is coming to that interface. All right? So two things to remember. The two planes refract with different powers, and that difference depends on the angle. All right, so you remember that. So here's a little picture. This is the moon seen from far away, and we are off here. And we're observing a ball, right? Just think of a large ball. At the center of the emission from the moon, the radiation just is coming straight out at us. But when you're looking at the limb, towards the limb, you're looking at radiation, which it comes and crosses at an angle, right? And so since the fraction of the radiative power, which is transmitted across this boundary, depends on the angle of this angle of the bend, you're going to see a difference in the amount of power in the radial and the azimuthal components. And so this is what the equations I've decided not to, because they're kind of gory looking, but they plot very nicely. So on the left panel, the red, look at the red there. There's two curves. The upper curve is the radial component. If you're thinking of the moon as a round body and there's a radial component, that component is the solid upper line as it transfers. And at the well-known Brewster angle, you're getting 100%. That means all of the power in the radial component crosses the boundary and you see it all. But at all other angles, it's less than that. The rest of it going back into the planet on the reflected ray. The dashed line is the azimuthal component, and it is always less. And so the ratio between the difference between those two is the apparent fractional polarization. Since the initial unpolarized ray in the surface has more of the radial component passing through the surface than the transverse azimuthal component. As you look outwards, this is the normalized offset. This is the center of the moon. This is the limb of the moon angle. And these curves show the apparent fractional polarization as you observe the source. It is true that if you integrate over the entire moon, you will see zero polarization. So I wasn't entirely wrong when I declared a long time ago that the solid body has to have no polarization. The issue is in detail. So this is actually very useful because you can use these curves to do planetary physics, because the fractional polarization as you go towards the limb that you will observe depends on the dielectric constant of the material. And this has actually been used. Okay, sorry, back up one. These are real, this is MeerKAT data. I think at L-band, forgotten what frequency I used here, just to illustrate what you see. On the left is a L-band image of the moon in a nice color coding. And it actually means something here. You know, we often use color in this radio business to impress the audience without telling what the color means. Here, the color is brightness. And the brightness is linearly related to the temperature in the Rayleigh-Jeans approximation, which works perfectly for radio. So you're looking at a temperature map of the moon here. I could have put these units instead of millijanskis per beam, I could have put them in Kelvin. And so you're looking, the reason that we can see that the outer boundary is perfectly round. It's darn well better be, right? We all know the moon is round, but it is somewhat elliptical in its brightness and its temperature. And that's because that's the equator. The equator of the moon has the sun shining directly onto it. And it's a slow rotator. You don't see you do see the phases of the moon in radio, but mostly at high frequencies. And this is because the time, the heating, if you put a thermometer a meter underground, you don't see the diurnal temperature change. It lags as you go deeper into the soil. The poles are colder and the equator is warmer, which is why the red is somewhat horizontally elliptical. And this is the fractional polarized flux, indicating in the way that I had tried to describe earlier. When you look at the center, there's no polarized emission. Both components coming straight out are passed with the same fractional loss. But as you go towards the edge, the radial component is stronger, and it gives you an apparent polarized flux. Now, so what can you do with this? All right. Well, planetary physicists love this kind of stuff because if you take an interferometer and you observe a planet, you look at the run of the polarization as you go from center to edge, and you can use that to determine the dielectric constant of the material which is doing the emitting. And this has been done, according to Brian, for the Moon, Mars, Venus, and Mercury. But for us as radio instrumentalists, because we absolutely know that the polarization has to be radial, except for whatever surface variations. I mean, if you go to a high enough resolution, you should be able to see some deviations due to crater walls and other non-spherically symmetric structures. We haven't tried to do that. You would need good brightness sensitivity. It might be kind of fun to try someday, but that's not the point here. You can observe one of these types of objects, and we've used the moon, and I will show you later, Mars and Venus, to measure the radial structures of the electric vector. Now, if for any reason your calibration procedures are incorrect, you will see or there is an ionosphere or some other instrumental effect that causes the position angle to be incorrect, like an incorrect assumed angle of 3C286, then your electric vectors will not be radial and they'll be twisted by some degree. I think that's on the next slide. Yeah. So on the left, this is again real data. This is taken with the VLA this time. If everything is correct, that you've done all your calibration correctly, and you observe a planet like the moon or Venus, the observed radial distribution of the orientation should be perfectly radial with no deviations. And a quick little program and integrates in rings can give you an estimate of the average deviation. But if there's some reason you have done something wrong, your software is broken, there's an ionosphere which rotates stuff, or your assumed angle for 3C286, if you're using the VLA, is not correct, you will get something that looks like this. And all of the vectors have been rotated by a constant amount. And so what you couldn't do, and what we have done in this, is this procedure here. We observe our polarization calibrator, which is the moon or Venus or Mars. We do our very best calibration based on an assumed angle of 3C286 of 33 degrees. You measure the average deviation of the radial field. And presuming that it is the same on the target source, 3C286, as it is on the moon, you can correct the position angle that you see on your target calibrator. And so basically, this is what we have done. Okay. All right, so now that's the introduction. This is what we now, but how did we ever get into this business in the first place? Well, when I came to the VLA in 1977, I was indeed told almost in exactly the words that Oleg told you. They said to me, and this is a quote, "We've just built this great big array and we don't know how to calibrate it. Why don't you go figure that out?" That's the only instructions I was ever given. It was a very different world in those days. You were thrown into the pool, and if you swam, they liked you, and if you sank, you had to go find another job. So that's what I did, and so the first thing I did was to check whether the famous calibrators that's in the bars at list. There's some of them here. Actually, had the fluxes that the bars at L catalog, which paper which dates back to the 1960s. And they said they did, and they weren't exactly aligned. And this was not a surprise. The bars at L data was taken very early, and it was nowhere near as accurate as what the VLA can do. So in order to track these things, to see if their fluxes are right as a function of frequency, extend the flux density scale, et cetera, et cetera, et cetera, I set up a regular monitoring program with the VLA about every year and a half. It started in 1979. And it's still going on, although I refuse to do this anymore because I'm getting tired of it. And to track these sources and determine their stability and their flux densities, and that resulted in a couple of well-known papers that Brian Butler and I published in the previous decade. And we use deconfiguration because it's a lot easier. Deconfiguration is all the antennas jammed in together because we weren't interested in resolving the structures. What we wanted to get were the fluxes, and to monitor the fluxes. And so you want low resolution for this kind of thing, because some of these objects, especially 3C123, it's quite large. All right, so that was good. And I only started doing these bands here, and I had nothing to do with the planets because we didn't have very good high frequency systems. But when Brian Butler came to NRAO in the early 1990s, he suggested that we should add, we were at the same time, we're implementing some high frequency systems that were not previously on the VLA. And he suggested we add observations of these 4 planets here. So we put those things in, and then being fairly thorough about this, I did the polarimetry of this stuff, and we got a rather large surprise when we looked at the planet Mars. So here's the data that I actually used. We had about 9, I think, epochs of observations of 3C286, of Mars at high frequencies. And this is the polarized flux. Not a very good map compared to the ones I showed you earlier, and I'm going to be showing you later. This is 43 gigahertz, which is a pretty tough frequency to work at. The VLA was never designed to work at those frequencies. The VLA antennas are only engineered to go to 15 gigahertz, and we push these things to 50. But the engineers, it's not their fault. They work really great at 15 gigahertz. They don't work very well at 50. But that's our polarized flux, and here's the position angle. Although it's not obvious from here, these radial vectors are about 4 degrees off from radial. And this was true on every one of the observations we took at 43 gigahertz. And it was also at 23 gigahertz and at 15 gigahertz, but by lesser amounts. And so we published a paper in 2013, and here it is. Which showed that the true position angle, 3C286, was not 33 degrees from 8 gigahertz to wherever. It actually rose up to about 37 degrees at 50 gigahertz. And as soon as we had circulated, a fellow named Chad Hall, who was at that time a PhD student at BIMA, the millimeter interferometer in California, sent me a very excited email. And he said, "This is really great, because we're doing polarimetry at 100 gigahertz or thereabouts at BIMA, and we were getting numbers greater than 33, and we couldn't understand what was wrong." And so this was very nice to get back. This is a linearly polarized system, and they also got about 40 degrees by 100 gigahertz. So this is all very satisfactory, and then we dropped the ball. We couldn't use the VLA's flux density data for checking this position angle at lower frequencies because being in the deconfiguration, we didn't have the resolution to resolve Mars. It's too small. And so the intention was to go and do it later. We never got around to it. Other things came up. kind of forgot about the project. And that's where Ben comes in. So a year and a half ago, in May 2021, I got an email from Ben, and it said, what can you tell, I'll paraphrase, what can you tell me about the position line of 3C286 at L-band? Because with MeerKAT data, we get some indications that it seems to be rather less than 33. There's a couple of ways this could happen. It could be that the dipoles that were used to calibrate are rotated by a few degrees. It's entirely possible. It could be an ionospheric effect, because as I'm going to show you later, the ionosphere is a very important contributor to the position angle of things that we see. But it sounds like a good idea that we should observe it with the VLA in order to check whether or not MeerKAT's polarimetry was having a problem. Now, the thing is that we can't resolve Mars with the VLA in L-band in any configuration. It's too small. So we have to look at the moon. And the moon is really too big. So we have to be in deconfiguration. And when Ben's query arrived, we were in deconfiguration. So very, very good timing there, Ben. But we're only going to be in deconfiguration for another week. So we had to do this on the hurry. And so a rush request was approved, and the antennas were actually moving from the smallest to the largest configuration at the time. But we don't need a whole lot of antennas for this. So what do we get? Well, first I have to show you the cool visibilities. I just love bright circular objects. So this is the amplitudes from 0 to 1,000 wavelengths, and you see the beautiful Bessel function, the J1 function that you get from a round object. And these are the long spacing. So this is 1 up to 3.5. That's the longest that we get in deconfiguration. And you see these beautiful, beautiful fringes. And now if you're good at looking at visibility fringes, you'll know right away the moon is truly round because we're still getting nulls all the way out to 3,500 wavelengths. So the thing is a beautiful round object. All right, I just couldn't resist showing you that. All right, so these are the images I got from the moon that time. This is the total intensity, and you see it's tilted, and that's because we did this in summer, and the moon's orientation of the skies turned by 22 degrees. That's all just geometry. And there's the polarized flux, and that's Q and that's U, roughly in the right orientation. If you're not familiar with Q's and U's, don't worry about it. You don't need to know this here. The answer is the right one. And we've done a lot of observing of the source since then, because right away it was clear that what Ben asked me, told me it was definitely correct. We were getting less than 33 degrees also with the VLA, so that was good. But I wanted to be complete about this, so I never have to do this again. So we got observing at S-band, C-band, and X-band, meaning all the way from 1 to 12 gigahertz, just to complete the circle. And we did with a different bunch of objects. So here's the 3 MeerKAT observations that Ben took. This is not relevant here. I'm going to show you at the end something about 327 megahertz, where things are very interesting. Just forget that for now. Here's the 2 observations of the moon with the VLA in our deconfiguration, and then an observation of Venus and Mars at a number of bands, because Venus and Mars are also good planetary bodies to do this work. But these are in A configuration, the highest resolution, because these guys are quite small. Oh, right. Okay. All right. So here's some pretty images. All right. On the left are the VLA images of the moon. And now in this case, I did not correct for the primary beam. So the thing is center brightened. The beam is 30 arc minutes for the VLA. The moon is 30 arc minutes for the VLA. And so you get a very significant limb darkening, which is completely artificial. But that doesn't affect the polarization. So radio vectors. This is Venus, all right? Nice and round, but there's an interesting feature, which I'll get back to in a moment. And this is Venus at 3 gigahertz, and this is Mars at 8.5 gigahertz. This is the southern pole here, and it's noticeably cooler. See, Venus is completely beautifully round and doesn't have any sign of darkening north, south, east, or west. But Mars is definitely darker in the south pole. It has a large ice cap. So again, we're looking at a temperature map in the total intensity. Okay, I'm going to show you the next one because it just that strange feature. This is the temperature map you might look at, right? And so there's a big cold spot. I didn't know about this. I emailed Brian Butler. I said, "What's with the surface of Mars? Is this correct? Is there a region that's cold?" And there's another one here also on the side. And he writes back right away. He says, "Yes," as if I'm an idiot and I should know these things. This one is something called Ovida, and this one is something like Thetis Regio, or maybe I have it backwards. These are elevated, high elevated plateau regions of Venus. They're cold because they're up, right? So somebody yesterday said, "What if we observed Earth from Mars?" Right? And so if Martians had a VLA to do this, they would absolutely should be able to see the Sahara Desert is hot, for example, during the time of year, I guess, and the Himalayas is cold. They should see the same kind of thing because these are temperature maps. But that's an aside. All right, so here, now the moon is big and it moves fast. It moves about a degree a day on the sky. So the moon is 30 arc minutes across. So every day, every half day, the moon is moved one moon diameter over. And so Ben made this marvelous movie here, which for some reason, I'm not seeing the little button that allows me to. Oh, okay. Oh, okay. Yeah, right. That's funny. There's a little. All right. So what band did you do this at? UHF? Yeah, 815 megahertz. So there's a couple things to notice here. These are background sources. The moon is moving this way, right? And normally in sidereal observations, these dots would be stationary and the moon would be heading off the other way. As you can see, these things go and they disappear behind the moon, and a little later they will reappear. And for one of my lunar observations, I had found a really close calibrator, and I was very pleased with myself. And after I took the data, I discovered that that big calibrator actually was occulted by the moon. So I was wondering what happened. All the visibility suddenly dropped to zero. And then an hour later, they showed up again. And it was a real problem because the short spacings completely obliterated the calibration. So you got to be careful. I mean, having a close calibrator is usually good, but sometimes it's not good. Anyway, so there's a double source. Now this lumpiness here is probably just.
It's a dirty matrix, so it's still side lobes.
Oh, okay. So he hasn't deconvolved this.
Yeah.
Only with MeerKAT could you get an image this good on an extended object without deconvolution. You can't do this with the VLA because we just don't have the number of short spacings needed to correctly. Without extensive deconvolution. So that's why it's easy for him to do it. It would have been horribly hard for me to do it. I'd have to deconvolve every single 10-second observation. I don't have the patience.
I did a very shallow deconvolution, but only on the background sources because the moon is where multi-scale clean fails absolutely spectacularly because the moon is a full box and it is not the Gaussian.
Yeah. Well, there's another way to do it, and you can model the moon as a pillbox and take those visibilities out, and there's software in apes to do that. It works quite well, but it's finicky. You got to tell it the size, you got to tell it the position, you got to tell it the flux. It takes all day. It takes the visibilities away, and you get left with virtually nothing, and then you put them back in again. Anyway, all right. So I hope this will actually stop now. Good. Okay. Now this is different than yesterday. Okay, so one more thing before we get to all the answers. Faraday rotation, the observed plane of polarization gets rotated when it passes through an ionized magnetized medium. The ionosphere is an ionized magnetized medium, and there is a well-known rotation of the plane of polarization of any wave that's passing through it. So the chi, the position angle you observe, is equal to the true position angle and a rotation given by Rm lambda squared. So this is a strong function of wavelength and which shows up typically at frequencies below about 3 or 4 gigahertz. Above those frequencies, you can completely ignore this effect, but below those frequencies for the ionosphere that we have on our planet, which is typically a few radians per meter squared, and I've seen as high as 4, but I haven't looked at very much data. It is important to note that at 1 gigahertz, 1 radian per meter squared rotates the plane of observation by 5 degrees. which may not sound like much, but in our precision polarimetry world, we're trying to get this correct to 1 degree. So any RM bigger than a couple of tenths of a radian per meter squared at 1 gigahertz, or 4 times less than that at the bottom end of the UHF band, because it goes as lambda squared, is an important thing that needs to be considered. So this is the detail, which I'm just going to pass over. I'll just point out, though, that if you had a uniform ionosphere and your calibrator and 3C286 had the same rotation measure, then you don't need to know what it is, because it's in my procedure, it's the difference that matters here. So that's what this little thing is. And there's models involved here. Okay. So what do we do about correcting for ionospheric rotation? Well, there is a program was written by a fellow named Chris Flatters at the VLA in 1990 something called TE-Core, which uses publicly available ionospheric data from a global network, and creates every 2 hours on a grid, I think it's of 10 or 15 degrees, the vertical total electron content of free electrons. And then you can combine this data with a magnetic field model of the Earth to calculate an expected rotation measure. And so this H program gives you all kinds of cool things. So this plot here, this is one of my lunar observations. This is the total electron content as a function of time. And the blue and the teal are the moon and the nearby calibrator. And this data was taken in the morning, so we can see the total electron content rising as the ionosphere is heated up by solar emission. This is the line of sight total electron content. So this is the vertical at the point where the ray crosses the ionosphere. This is the total, which takes into account the angle in which we're observing. This is the magnetic field from the model that is passing through. And the bottom one, which is the one we want, is the estimated ionospheric rotation. That should be a rotation measure. Here it goes from 1.5 to 3.5 radians per meter squared, which is a significant amount that needs to be accounted for. Now, the question is, how good are these corrections? I mean, this is a fairly crude model. We were using a very simple dipole model of the magnetic field and these sparsely sampled total electron content data. So I did, for that experiment, I did a very simple thing. It's a 5 degree, so there are 170 stations, global stations contributing to this model in this particular database. So on the left, on the little chart, is the time, the local time. There's the predicted rotation measure. This is the elevation. This is 3C286, right from the time that it rose off the ground up to the time VLA 3C286 nearly goes right through the zenith. So there's an enormous range of elevation. This is the position angle without any correction. And it averages 33 because that's what I told it to be. Okay. But because the ionosphere rotating, it actually starts off at 26 and ends up at 36. Okay. But the average over this period of time is 33 because that's the calibration offset that I told it to be. And then with the corrections of TE-Core, they're all absolutely within one or so degrees. So this was very encouraging. And so 2 days ago, I tried it on some MeerKAT data. And here we did not get such good agreement. So Ben and I are still thinking about this. The MeerKAT data for one experiment at the UHF band, the observation of 3C286 showed a constant position angle, didn't change. But TE-Core and another program that Tony Willis has done, Albus, both predicts a change in the predicted rotation, which we do not see in the data. But that's just an observation. Yeah.
Auto-corrected.
Well, that's corrected. Yeah. Yeah, maybe I corrected and I didn't know it. I mean, there are, I really need Ben to reproduce it from his way of doing these things, make sure that I didn't somehow auto-correct it.
Because it's differential, as you say, you're only sensitive to differential.
Not in this case. There's no differentials here. This is just 3C286. So that you see, this is the time variability I'm looking at, not what the correct angle. I mean, this is not the correct angle.
Yeah,
it's the one I told it to be. But what I was interested in is that 3C286 itself is not going to change in a 3-hour period. And so you can take whatever, I mean, I could have made that 150. And what I'm looking at is what happens in time, because the only thing changing is the path length through the ionosphere.
Is that the same reason why the correct angle here is not 33?
Yeah.
Because here you force it 33 and there's some overall also.
Yeah, right. And so there's an offset, which I would get by observing the moon. Right, okay. Okay, so that's where that is. We think, based on a single observation, that this program TE Core is working for VLA data. The density of stations in North America is very high. Maybe the issue is a sparseness of data here. We have no idea. That's just a complete guess. Oh, one thing I need to point out, this TE Core program, thanks to my getting some MeerKAT data, I was looking at the TE Core predictions for the MeerKAT observations, and we noticed that at meridian transit, exactly within 1 second of meridian transit, TE Core claimed the rotation measure changed by 1 radian squared. And it did it for every single source as it went through meridian transit. So I said, this is not physical. So I went to Eric Bryson, he's the king of apes. And I said, there's something wrong with TE Core. And it didn't take him long to find it. TE Core has been miscalculating the azimuth of the observations since 1999, and nobody noticed. Now, to protect the reputations of people who used it, the corrections for the VLA are very small, typically 2 or 3 degrees. You've got to be looking carefully to see this kind of stuff. It was only because we were observing in the north here. The issue is in the north when you observe in the north.
No Nobel Prizes will need to be revoked.
No. There are other issues, but that's it's amazing the things you learn when you look at data carefully. Right? You can't do this with a pipeline. Right? You can only do these things by looking carefully. Oh, I'm not disparaging pipelines. I'm saying pipelines only give you what you tell it to do. Okay. All right. So here's the MeerKAT observations that Ben took. This is where in order for us to do it, I had to get Eric Bryson to implement linear polarization, linear polarized systems. That was kind of fun to do. And I already mentioned that, so we can skip past that. So these are the final results after TE Core. So the upper plot shows the fractional polarization of 3C286, including the low frequency UHF MeerKAT data. That's the black position there. So in terms of fractional polarization, when you're up at 12 gigahertz, it's 12 point something percent. It slowly declines until you get to about 1 gigahertz, and then the bottom drops out of 3C286 fractional polarization, which I knew this had to be because at our 327 P-band system of VLA, I've not been able to detect any polarization at all. So by 550 megahertz, it's down to 2.1%. And by the time you get to 327, there isn't anything, which is a bit of a problem for doing polarimetry at low frequencies, because we essentially have no polarized calibrators to check our results. This is the position angle, and it really is 33 degrees at 12 gigahertz. So, Big Nell and Sequest got it right. It's like 32.5 actually, but their accuracy was 1 or 2 degrees. We have fractions of a degree accuracy in this. It is very constant until you get down to about 4 gigahertz, and then it starts to slowly roll off. There's a little bit of disagreement around 1 gigahertz between Ben and me, and we've still got to resolve some of these things, but the disagreement is the order of 1 degree. So it's not a major, and 1 degree is the accuracy we're working for. And then it just drops dramatically when you get to the UHF band. And so these are just slight blow-ups of the same area, so nothing too interesting there. This is versus lambda squared. So if this was a simple screen, so why is 3C286 position angle changing so dramatically at low frequencies? This is a Faraday rotation effect of some sort. It is probably due to ionized gas in the nuclear regions of 3C286, which is rotating it. It's not very large, An RM screen will give you a straight line on a plot versus lambda squared. And so the upper frequencies are fitted roughly by very close to 0 radians per meter squared, which was the assumption. But the low frequencies, it rolls over into about -3.5 radians per meter squared. However, it could be due to other things as well. It could also be due to depolarization effects within the jets of 3C286. It could be due to beating between different components of 3C286 that we don't resolve. Right? Because when you have a big B and you're looking at a complex source, you're getting a kind of a vector sum of everything that happens in the source as it arrives to us. So this is what's called beam depolarization, and it's a very difficult thing to get around. The only way you can clearly figure out what's going on here is to have VLBI scaled polarimetric interferometry to resolve out all the elements of the jet of the structure and to see what's actually going on. Lexi's doing this kind of work for Pictoray, and Lorado, who all of you I think will know, used my Cygnus A data to do a very fine piece of work on that. Okay, so we're nearly done with this, but there's something else I wanted to show you. I talked about emission from the planet, right? Crossing the boundary. Somebody should have said, what about reflection? What happens with a ray coming in from outside, striking the moon's surface and reflecting? Because that also will suffer. The reflection will suffer a change in polarization properties. All right, so that's the introduction. So here's 327 megahertz at the VLA of the moon, right? There's the eye map. Something important is being hidden here. There. If you look at Q, there's a white dot down there in the corner. And it's more obvious in U. There's a black dot where it should be white. Okay? And so here's the polarized intensity. And then there's a big spot of emission where there shouldn't be. So I had no idea. And so I told him when this was many years ago now, and I asked Brian Butler, what could possibly be going on? He's the planetary expert. He says, I don't know, there may be something on the surface there. So he was peering at moon maps, optical moon maps. He said, I can't see anything special. But then I was at the SKAO office, and I gave not this talk, but a talk on our efforts to do polarimetry at 327 megahertz. And Justin Braid was in the office. And so I don't know if he's known to you people here, but he immediately said at the talk, he says, where was the sun during these observations? And boy, I should have known this. If you draw a line from the center through that black spot, it goes right through the sun, right to the sun. This is reflected solar radio emission. And because it's reflecting off the surface and not coming up from underneath, the polarization modification is exactly opposite. So it turns into a circumferential field rather than a radial field. And that's exactly the orientation. You can't see very well here, but that dot, the little purple line, is exactly at right angles to the emission coming from the planetary body itself. And we've seen this with the VLA data much more weakly. This is a very obvious effect at low frequencies. It gets less because the sun is a weak emitter at high frequencies, but it's a very strong emitter at low frequencies. Okay, so that is the bottom line of this. MeerKAT and VLA gave very similar results. The EVPA of 286 definitely declines with decreasing frequency. We're pretty confident what it does down to 1 gigahertz. Below that, there are some uncertainties, mostly due to the correction from the ionosphere, which have yet to be worked out. TE core corrections VLA are good, but that's based on a single observation. So I'm hoping to get a summer student this year. I'm going to give this poor girl a ton of old data of strongly polarized objects at all kinds of different places and times, because we need to be able to tell people what is the reliability. TE core is a very simple-minded program, but for 1 gigahertz, it may be entirely sufficient. For for the Dutch in their low frequency array, because I know they're working on this problem. And for you people with UHF, you need to do a little better. And so there's, you need an ionospheric expert to perhaps help us out here. That's what I said there. Okay. Now, before I go on to the ngVLA business, does anybody have any questions on this aspect of things?
Two things. The one question is, what about the gas giants? Jupiter?
Oh, you can't use those. Yeah.
Is it the dielectric constant?
Well, Jupiter has no solid surface anywhere.
So the gas itself doesn't have this effect.
No, it's and it also has an enormously powerful radiation belt around it. I mean, we have observed Jupiter as part of the flux density business, but I quickly gave it up. It's too big, too complicated, and not useful. Venus can only be used for this work up to 4 gigahertz, because everybody knows Venus is a thick atmosphere, right? Well, it turns out it becomes optically thick for radio radiation above 4 gigahertz. So as you go up in frequency, the planet body just slowly disappears. And you just see the atmosphere, which is dominated by emission from all kinds of molecular transitions. I don't know anything about that. And Mars is good at all frequencies. It has no ionosphere, no magnetic field, and its atmosphere is completely transparent. He said he had another one. Sorry.
Yeah. I think it reminds me of CAT 7 days. We in our very first sort of round, and we realized we had the H and V swap.
Oh yeah.
How do you know which one is H and which one is V, and how do you detect that they got it the right way around? So one of the case schemes we had was to, of course, CAT 7 could go down 2 degrees elevation. We filled it down. I thought that you could use the ground scatter. I think the use of
because it's polarized.
So it's exactly like this.
Yeah.
Basically going to be vertically polarized. Everything that bounces off. And then whichever is stronger, you can then say, okay, it's the right way around.
Well, it's very imaginative, but that's the hard way to do it. Just observing 3C286 for a few hours is all you need to do, because even though we don't exactly know what its position angle is, we know well enough. And that's what I did to figure out, for the APE's purpose, how to calibrate your data from MeerKAT. And thank you very much for giving me this extra 3C286 data, because otherwise it's quite a problem. You had a question?
Yeah, so with your observations of the moon, you had the sort of limb of the moon kind of in the edges of the primary beam.
Yeah.
Do you have to worry about sort of polarization if it's in the
yeah. But for the VLA, at the half power point, the effect is a couple of degrees. And we also observed over a long period of time. So the thing rotates around that, and the polarized beam, it changes sign as you go, as you rotate around the beam. So it averages out, and it's small, but it is a source of error, which is why I really much prefer to use Venus and Mars for this work, because there's no beam effects with those. They're absolutely tiny, arc second, rather than 30 arc minutes. Yeah, so it's a good question, and a real accurate effort would use this A projection business, but it was just not justified for our purpose.
There's a hand online. I see a raised hand from Paul. Paul, do you want to unmute the last question?
Sure. I don't know if you can hear me.
Yes, you can.
Okay, great. It was just a comparison on the NRAO website. There are whole lists of polarization calibrators, and they give a range of values as a function of frequency. Do your values align with that? I'm more curious what they list is accurate or not.
Okay, so virtually every calibrator source, polarized calibrator source that we know, is time variable in its polarized characteristics. Only 3C286 is the only source that I know which is highly polarized and invariant. All the others are variable. So when you say polarization calibrator, what determines a polarization calibrator for MeerKAT?
No, just on the NRAO website, they have known values for 3C286. I'm just curious if your values align to what they publish as the reference values.
Yes. So I don't know if they're updated to in the light of what we're now recently learning, is only 3C286 listed, or are there other
There's
ones?
just few listed.
Other ones as well.
3C48 at the higher frequency.
Oh, yeah. So the 3C48 is a very bad source to use for polarization calibration because it had an enormous flare back in 2018, and its structure and its polarization changed dramatically, and it changed the function of time. And this was at 40 gigahertz that we noticed this. So one has to be very careful by using supposedly known values for these sources. They're all variable, except 3C286, but that changes with frequency, as we've now learned.
Okay, one more question. I see a hand online from Boom. Boom, you want to ask a question?
Yeah, sure. Thanks, Rick, for a great talk. It's good to hear from you again since 2012 in NRAO summer school. My question is, yeah, that was a long ago. My question is, does the polarization intensity of the moon change at all over time? Because if I understand, it's not in perfectly synchronous orbit with the Earth, right?
That could only depend on the surface properties of the emission. I mean, the moon does wobble a little bit from our perceived point, but a planetary physicist would have to tell this, but it's not going to change very much, I don't think, because it takes quite a large, but to put the answer a different way, it has to be radial, whatever the dielectric constant is, except for whatever surface features are making it non-radial. So at least to the approximation of a spherical body, I think the moon is pretty close to spherical.
And we taper away most of our long spacings anyway, because they're not applicable to the work.
Yes. So I mean, if you over resolve it, you're losing the signal you're actually looking for. So it's the large scale stuff. No, so I don't think there's any issue with the moon's apparent change of perspective. But a planetary physicist could say otherwise, but I doubt it.
Cool. Thank you for all the questions. I had a comment you just mentioned. Well, you have to mention the same thing now. You said if you get enough resolution, you could see craters.
Yeah, we should.
Ben has maps showing exactly that.
Yeah, okay.
You do see craters in polarization.
So you must do this at F-band, I think. It's a great.
You can see them in the UHF maps if you make a multi-frequency synthesis map as well, but they're most spectacular in this band.
Yeah, and the reason for that is that the brightness of the moon goes up with the square of the frequency because it's a thermal object. So if you want good flux, you need to go up in frequency. But then, of course, even for MeerKAT, moon gets too big. And so even at your S-band, you're starting to lose the edge of the rim of the moon because it's getting towards the null. Yeah. I suppose in S3, it must be right out in the null.
You can't see them really.
Okay, so we have a couple minutes left, so I thought I would briefly update you on the ngVLA. I need to first tell you that I have almost nothing to do with this project. There is a very intensive effort, as you're about to see, from NRAO and from and many other groups working on this project. This talk is Eric Murphy's talk. Eric Murphy is the ngVLA project scientist, and it's a talk that was given internally last September. Therefore, since it's internal, it's filled with jargon, and not all of the jargonese can I decode. But it gives you a pretty good overview of what the intentions of the project are and its current status. So the overall idea, this is a high frequency project. It is not focused on low frequencies. It goes from 1 to 120 gigahertz, but the science cases are very much tilted towards thermal imaging, planets, protoplanetary disks, structures of this type. The basic, so thermal imaging at milliarc second scales. That's a nice little summary. The overall goal is 10 times the sensitivity we have now, and ELMA. See, this is a bridge to ELMA. You might also look at it from that point away. 10 times the resolution, 1 to 116 gigahertz, and an absolutely astounding number of 244 18-meter offset antennas and 19 smaller ones centered in the VLA site and concentrated in the US Southwest. It is, of course, traditional for everyone to show their sensitivity plots, and it's always necessary that your sensitivity plots are better than anybody else's. So on the left here in the pink is the ngVLA's predicted sensitivity if we get to build the whole thing. In the purple underneath it is the claim sensitivity SKA taken from their webpage. The orange stuff at the bottom is the VLA currently. On the right here is ELMA and ngVLA, and these greenish teal colors are where the atmosphere is optically thick. This is 60 gigahertz absorption line to the oxygen, atomic oxygen, which completely cuts off while observing. And over here is a resolution plot with all kinds of different kinds of instruments. And of course, the designers want the ngVLA. The focus on thermal imaging is very clearly shown by this horizontal bar, terrestrial zone planet formation 1AU. So this area, much of the science case is focused on planet formation, planetary disks, galactic thermal structures. So you see, this is it completely dominates that zone. Okay. This is, you don't care about this. This is the organizational chart. There's at least one South African in there. Okay, so this is more important. The idea is to have two frequency doers, an A and a B. The A is the L band one that goes from 1.2 to 3.5 gigahertz. And the B doer holds all the rest. And as everybody sure realizes, L band is low frequency, much larger system. And so it's organized into these 6 bands with the two doers with a very wide bandwidth at the highest frequency, 46 gigahertz in the analog data. The distribution of the antennas, there's now these numbers are fluid, right? Because as everybody here should know, when you ask a group of people to sit down and design an array, the knives are all on the table. People who are pulsar people and people who are interested in low surface brightness line emission are in one corner arguing for all the antennas to be close to in because they don't need the resolution. And other people, the camp that I'm in, think all these antennas close together is a huge waste of resources and they need to be distributed so that you can get good imaging on large, small angular scales. There is no way that this telescope is going to have movable telescopes like the VLA and ALMA do. This is a wonderful way to do things. It has some real advantages to allow you to shape the array to match the science you want. There's some disadvantages as well, especially when you're observing time variable sources. But there is no argument that this ngVLA will be a fixed array. It simply can't move 250 antennas around 1,000 kilometers of space. It's just not in the cards. So that nice idea was given up. Okay, now if you're familiar with the US map, this is the United States, there's Mexico, there's Canada on the upper left. That's where I come from. I'm from British Columbia. These little dots are one of the trial arrays, but this is under constant change. And so that there's, because there will not be a decision, I'm sure, on where antennas are until the trucks carrying the concrete actually pull up. So, this is the ongoing struggle. There will be 2 or 3 antennas at each out stations, one out here. So the VLBA stations are going to be replaced with ngVLA antennas. The old VLA antennas, I'm not sure what will happen to them. Over up in the upper left is a slightly larger. There's half a dozen stations that will be in Mexico, and the Mexicans are eagerly part of this project. And then there's a real zoom in under the plains of San Agustin, which is the high plain on which the VLA sits. It's a 2,200 meter high former lake bed during glacial times.
What's the non-exact corridor?
I have no idea. Hawaii. Oh, Mauna Kea. Not at Mauna Kea. Yeah, I never thought to ask him about this. Yeah, that's a good question. I'll have to ask the boss. I don't know these things. Now an important part in U.S. Development is to get a high recommendation in the decadal committee. So I think everybody here is aware that every 10 years, the United States, a high level panel reviews all of the large scale proposals for investment of National Science Foundation, Department of Energy funding for astronomy. And it's extremely important to be high on that list in the category that you're in. We're in the big category, of course. This is a $2.5 billion project. And we got to second place, which is what the goal was. The major optical telescopes, TNT and the GMT, were first, as everybody had expected. But they have, especially the TNT, has very significant political problems locating their telescope on Hawaii. And it's completely unclear when construction of that can begin, or if it will ever begin on that site. So I can't get into that because I'm not an expert, but I did go to the AAS meeting and went to their town halls, and the situation is very murky. So it's a long running business. Okay, what do we got? Okay, time scale. So what's important here is the prototype delivery. So the NSF has given NRAO a $20-something million contract to build a prototype high-frequency telescope, offset 18-meter, just looking very similar to the MeerKAT antenna and the SKA antenna. And you can see a sketchy picture. This is now under construction, and the German company, which got this contract, and they are currently testing panels and assembling the parts, and which will come to the VLA in, I think, about a year, in which it will be placed on the same pad that was used to test the ELMA antennas. And then it will be integrated into the VLA's observing schedule, and we will do all the antenna tests, pointing, holography, sensitivity, all the kinds of things you need to do to prove the antenna. And that is supposed to be done by 2026. And then based on those results, the optimistic schedule, I suppose, is construction starts in 2026. If the NSF agrees to fund this, because that, getting a high recommendation in this panel does not guarantee that the project will be funded. It just says the panel thinks it's worthy. NSF still has to find the money. And 2029, early science, and a date so far out that is well beyond my horizon and maybe even some of yours for full science operations. And you got to believe it's an optimistic schedule, but I could not make any comment on that sort of thing. Yeah, let's see what else we got here. Oh, no one cares about this. Of course, like everybody else, we couldn't have, but there's a very, very intensive round of meetings to hone the science case and to keep the case alive. This is no different than what SKA has been doing for many years. And this is on computational astrophysics in the ngVLA era. Oleg, you recognize anybody in there? Okay. Yeah, I don't even know where this was, but so it's the start of face-to-face meetings again. All right, moving on. You guys want lunch? I want lunch, so we'll get this over with. There's the antenna development, and there's some details in there that are not important for this group at this point, but they're all quite interesting. One thing that is of interest is that Tony Beasley, our director, has told us all very clearly at the VLA site that when that prototype antenna arrives and is mounted and ready for testing, its needs take precedence over everything else, right? So that's a very clear signal. Doesn't matter what breaks, what doesn't work, or who's angry today. Testing of this antenna is the highest priority. Okay, for heaven's sakes, I don't even know what's on that slide. We'll move on. Well, these kinds of things are familiar to you. It's the same geometric arrangement that MeerKAT, SKA are using. And the details I wouldn't know anyway, so we'll just let that go. Computing, all summarized in one page. And the only thing I think which is important to point out is that we will be keeping all visibilities. It is part of the plan. So there's going to be no pipeline and then throwing away data that you wish you had later when things don't work on your pipeline correctly. We're example. And there's a couple interesting numbers here. 4-hour observation of a full field, full polarimetry, is 109 terabytes and 1,000 cores. I'm not sure cores of what to process in a few days. So so you can rapidly get behind unless you have a lot of cores. So they're talking about I think that's billion core hours. But they seem to think that with commercial off-the-shelf clusters, this is a solvable problem. It doesn't have to be solved for 10 more years. So hopefully, but this is an area that I do not know much about. So we'll just skip it. All right. This is, there's ongoing development. There's a number of internal groups. There's a number of external meetings, all of which is ongoing to keep the flame alive and keep the project moving and to keep the momentum up. There is, what this means is that we've been getting millions of dollars from the National Science Foundation to develop this concept. This is really quite surprising to me. I didn't think the NSF could spend that kind of money on a project that they have not yet formally approved. But they seem to be sufficiently impressed and believe in the observatory's capabilities that they're willing to funnel this money to us in order to develop this system without necessarily promising that they will ever allow it to be built. All right, now where there's, this doesn't really matter anywhere because that was already last year. This is a Tony Beasley in his presentations always likes to put in the next 120 days. This is what we're doing. But since this talk was written well more than 120 days ago, it doesn't really matter. But this is one that's important. This is the only slide of which I put in. I asked the project director, the science director, what can I tell you about time scale and who's paying for this? So this is what he gave me. The current estimate is $2.3 billion for this complete array. 75% funded by the US, 25% from foreign and something he called multi-agency partners, which I'm not quite sure what that means, but it might mean the Defense Department or commercial interests. It's not just about astronomy these days. That's a guess. I bet you I'm right. And we are actively seeking partnerships. And so our top administrators are talking to the Canadians, the Mexicans, the Japanese, maybe even not the South Africans, I don't know, to be part of this consortium to build. But unlike the SKA, this project is a US project. It will be managed, run, and directed by the National Science Foundation through the NRAO. Right? So we have what Tony once said to me, trusted partners. They will be given a seat at the table. They will have a unique section to work on, but there's no question about who's running the ship here. Operation costs, this is a good one. $93 million per year is what they're aiming at, which is really impressive if they can do this, because that's only 3 times what we're paying right now to operate the VLA and the VLBA. And despite the fact you're getting more than an order of magnitude improvement in terms of sensitivity, and more than that in some other characteristics.
Does that include compute costs?
I think so. Yeah. That's the implication from the email I got. I did not ask that specific question, but that's hopefully that's right. Yeah. It's an open skies instrument. That's the plan, right? Open skies meaning the only barrier is the quality of your proposal, whether or not the committee. However, there was a but attached to the message, though. Whether it's open skies depends on the SKA being open skies to the consortium that NRAO is trying to put together to build this telescope. And these discussions at a level way above my pay grade apparently have begun. And that's all I can tell you there.
So if an astronomer is not an SKA,
that might be a good question. Yeah, so that's the one in the Venn diagram. There's a third piece. Somebody in a country not attached to either project, and if the 2 projects cannot agree with each other on open skies, what happens to them? I don't know. Okay, and that's all I got. It's time for lunch.
Thanks very much, Rick, for a fantastic talk, or in two talks.
Yeah. Half talks.
2.5 talks. Do you have any questions? Do you have any questions from the remote? Remote, raise your hands, please. Yeah, Andreas, I see you has stand up.
Yeah, hi, Rick. I've actually two questions. One question is, how do they envision the transition phase from like what will happen with the VLA and the VLBA? And second question is, I've seen that there are 3 remote stations at the VLBA stations, right? However, if you want to do like high precision astrometry, having 4 remote stations would be really much better than having 3, because you can have your target and 3 calibrators, so you can basically map phase gradients in 2 dimensions on the sky. If you have only 2 calibrators, you can do that only in 1 dimension.
Yeah, so let me answer the latter one first. I know there's a lively discussion going on amongst those involved in this, whether there should be 3 or 4 stations at each of the remote VLBA stations. So this point is, of course, well understood by people like Craig Walker, who is arguing for more stations. What was the first one? I've already forgotten. Give me that first.
Transition.
Oh yeah, transition. Oh yes. All right. So there is a transition plan. Of course, I always find it amazing. They write transition plans before a single antenna has been built. But it's always good, as they say, plans are essential, but planning is essential, but the plans are useless. So Tony at one point was saying, as soon as construction begins, we will simply turn the VLA into a pulsar machine at S-band and freeze the array in the C configuration, and we'll just do pulsars. However, I think he has been convinced that this is not a wise plan. The array will take over 10 years to build, and you simply can't cut out the world's biggest and most effective centimeter astronomer, a centimeter facility. So the plan, as I understand, is that we will continue to run the VLA in the current way that we're running it, but I am certain that they'll be looking for ways to cut the operational cost. One of the really significant problems that everybody knows about is that we have to have a greatly increased staff to implement and test these incoming new antennas. And we can't have those people working most of the time on old VLA issues. So there are going to be a ton of new hires once this project is begun, if it's begun. And I'm sure they'll be looking for significant cost savings to run the VLA, but without, hopefully, not seriously gutting its capabilities. But as I said earlier, I'm not a part of these plans. I just hear secondarily and from Tony directly when he visits.
Okay.
We have one more question online from Stabile.
Hi, Rick Perley. Thank you very much for this talk. It's very enlightening, and it's also good to hear about developments with the ngVLA. I would like to find out specifically about that last bullet point on this slide. When you say that SKA, this will all be dependent on SKA being equally available. I'm not sure what that means. Is that are you referring to consortium members of ngVLA having dibs on dedicated observations with the SKA, such as what we have with the MeerKAT large survey project? So what does equally available mean in this case?
Yes. The answer is I don't know. These are the words specifically written to me by the ngVLA project scientist. And the implication that I understood from what he wrote was that we want to be an open skies project, open to everybody, and we're hoping that the SKA also is an open skies project so we can avoid these tit for tat kind of things, and that discussions are ongoing. But he did include in his email to me something about ngVLA consortium members having open access to SKA. But he did not define, and I did not ask specifically what that meant. But certainly the implication of the message was This is very early times and the management people are just beginning to discuss this. So I'm sorry, I can't do better than that.
All right. Thank you very much.
All right, well, if there's no more questions, it is getting way past 10 minutes lunchtime, so let's thank Rick again.
Okay.
Thanks everyone for coming. See you next week. We'll have EVPA, talk about some very interesting imaging results. So please join again. See you then.